This is going to be the final screencast here. I'm going to combine learning targets 6 and 7 in the same screencast. And I'm going to start with learning target 7 because some of you have said that you don't understand Le Chatelier's principle. And one thing I want you to know is that you'll notice on that learning target I put an asterisk because I didn't know if we'd have enough time to fully cover that. And even if I were to teach till the end of the school year, I wouldn't have gone into that learning target because we just ran out of time. It actually takes a lot of time to understand Le Chatelier's principle. There's a lot there. And in your book, I think you'll even see it says kind of like an advanced topic. You'll get that in chemistry, but there's simply not enough time. There was one thing I wanted you to take away from that learning target, though, and I did ask the question on the quiz you guys took last Friday, and that is this: that know that reactions oftentimes are reversible. So that's typically, again, you'll see a chemical reaction with an arrow going to the right, but later you'll see kind of a double arrow, and that's kind of saying that reactions can go forward, which is the normal way we think of it progressing, or it could be reversed. So the thing I wanted you to know about learning target 7 was that reactions often are reversible, and when you look at the reverse reaction, things are opposite. So the example we used was the formation of water, and then the opposite of that is splitting water back into the two gases that made it up. And incidentally, I think this is the same thing that Lavoisier is looking at in that movie as well. He looks at splitting water up with electricity into the two gases that make it up. Um, so with that example, what we looked at then was, okay, the formation of water, which we saw in class demonstrated, that was exothermic. And it's also a synthesis reaction. So if we look at the reverse of that reaction, well, what's the reverse of a synthesis? The reverse or opposite is decomposition. If the reaction of the formation of water is exothermic, what's the opposite of that? The opposite is endothermic. So that's what I wanted you guys to take away from learning target 7, was that reactions are often reversible, and when you look at the reverse reaction, things are opposite. Okay, so let's look at learning target 6 then. And even in learning target 6, we've had to cut some things out. So you'll see we've had a few sub-bullets for learning target 6, but we've had to kind of cut some of that out. So I do want you to understand the difference between exothermic and endothermic. So we talked a little bit about that, but we're not going to get into necessarily classifying things in terms of endothermic or exothermic. I guess I could have you classify it in terms of if I kind of described what was happening, such as energy being absorbed or emitted. In that case, I could ask you if it was endothermic or exothermic. But there are other ways in chemistry which you'll learn about how you can tell whether it's exothermic or endothermic, and that we're not going to get into. So again, in general, just know the difference between exothermic and endothermic. Exothermic means that a reaction is releasing energy, whereas endothermic means that a reaction is absorbing energy. Okay, so then the main thing that I'm trying to get you guys to understand is how these different factors affect a reaction. And reading your guys' comments on the reflections, I think one thing I want to clear up is that all of these factors can either increase or decrease. So I think, based on what I'm reading you guys, the feedback I'm reading from you guys, I'm getting the sense that some people might think that, for example, a catalyst can only increase a reaction. Well, in reality, we could take away a catalyst, or, like your book says, add what's called an inhibitor, which is the opposite of a catalyst, and that would decrease a reaction. And we can do that with surface area or temperature and so on. So we've got these 6 different factors. Some places will kind of combine these 6 into 5, and with each of these factors, we can either increase or decrease depending on what we're doing. So you guys looked at the simulations. That was one thing you did, and some of you said that was helpful as well. So we'll kind of go through that again. I know this is just repeating for some of you guys, but I'm assuming that for those that are actually looking at this, they had trouble the first time seeing that, or maybe you weren't in class that day so you didn't see it. But we looked at surface area both as a demonstration and a simulation, so let's look at it again. So when you do the simulation, you see three different pieces, three different particles for this reactant. The other reactant, which is controlled, is this, so we're always using the same amount of this reactant. Another thing I'll say about simulations is oftentimes, I get the feedback that where people say, I didn't know what to do. I open this simulation and I have no idea what's going on. Just realize that's actually intentional. A lot of times when I look at simulations, I have the same thoughts that you do, and that's the point of a simulation, is just to really experiment, try things out. You got to kind of figure out what to do, and then once you figure out what to do, you got to figure out what that means. So that's all part of the scientific process. The way I look at it is a simulation really just speeds up what you might be able to accomplish if you were to do many experiments. So and the nice thing about a simulation is it's often set up to work. And sometimes if you were to do a simulation, an experiment, depending on what you did, like we did with that one I talked about earlier with the reactivity of metals, there were some issues there where things didn't work. So whereas if we did a simulation of that, they're going to set up a simulation to make it work every time. So anyway, let's get on with the simulation here. We've got three different particle sizes, and we're going to test them one at a time. So many of you that did this said what happened. Okay, I'm putting this in the beaker. At the same time that I put that in, I've added this other reactant, and we can watch this happening. So one thing you'll see is that these reactants are kind of jostling around. And this is something else that Einstein discovered. He kind of mentioned it in the movie, or you'll see it in the movie later. He kind of came out with a number of things that benefited science, ideas, and one of these ideas is actually proving that atoms exist. Einstein was looking at a piece of pollen under a microscope, and he noticed that it was kind of jostling around like those reactants are. And so that kind of led to the proof that atoms exist. So you guys saw how long that took to react. Now if we kind of take this piece, if you can imagine, we kind of take a chisel to it and we kind of break it into some smaller pieces, you'll notice that things react much quicker, especially to begin with. Now, every now and then you'll kind of see that based on where this reactant is, it may take a while to get that last little atom, but initially it's much quicker, and overall it's probably quicker as well. And then the next one, now we're getting things to happen really quickly again, especially initially, but it might take a while to get these last couple. But the idea is, the smaller the piece, you're actually increasing the surface area, and by increasing the surface area, you're increasing the rate of reaction. So you saw that with the demo I did with sugar. I took a sugar cube and burned it. Takes a while, not very spectacular. I took powdered sugar, and you can tell if you were there in class, that burns right away. You get a much more spectacular reaction because you've increased the rate of reaction. Okay, so that's surface area, and you can go through each of these other ones. I'm not going to do that, but we can look at concentration, which you guys also looked at in the clock reaction. And you can look at temperature. One thing I'll mention on concentration that Kaylee noticed in the clock reaction, and I think somebody else noticed it as well, was that when you guys, what we did in that clock reaction, we actually decreased the concentration. If you remember, we started with 16 milliliters of solution A, and each trial you guys did, we took away 4 milliliters. So by the last trial you did, you only had 4 milliliters of solution A. So there in the lab you guys did, we decreased the concentration. And by decreasing the concentration, I think everybody that recorded the times saw that the reaction rate also decreased, which means that it took longer, it took more time. That's what that's saying. So one thing that Kaylee and somebody else noticed was that even though we took away 4 milliliters every trial, the amount of time that it took for things to react did not change by an equal amount. So therefore, those students noticed that, hey, this relationship between concentration and the time that it took to react, it's not linear. And in fact, it's exponential, which you'll see again in more advanced chemistry. But that was a great observation, and I got to give Kaylee an Oliway ticket for that, because that was again, one thing that we started the year with was making good observations, and no matter what level you consider yourself, scientifically to be at, that's something everybody can do, is make great observations. So hopefully you guys take that away from this class. So let's go ahead and what was one other one I wanted to look at? We looked at concentration. We looked at temperature. So this was going to be the other part of that lab that you did. The clock reaction was looking at temperature. So once again, we can put these reactants in a beaker. Right now we've got whatever temperature this is. It says 21 degrees Celsius. So as we put these into the beaker, you'll notice that the blue and the red reactants, when they collide, we're talking about collision theory here, when they collide with sufficient energy or orientation, we'll be able to form a product, which you see in green. And you'll notice that when we have a lower temperature, these reactants and products don't move around as much. So there we go. So our reaction's finished now. So we're going to reset this. We're going to crank this temperature up to about 84 degrees, 4 times what we had in terms of Celsius, that is. So we're getting there pretty close. There we go. Oh, okay. We'll call that close enough. So we'll do it at 83 degrees, and you'll see, wow, we got a lot more jostling around here, and we had those products forming right away. So if we increase the temperature, we increase the rate of reaction. Okay, so that's really, again, what I wanted you guys to get away from Learning Target 6, was really understanding how those factors affect the rate. And remember that the rate could be either increased or decreased. And again, you got to think about how to do that. Okay, with temperature, we can decrease the rate of reaction by decreasing the temperature. We can also increase the rate of reaction by increasing the temperature. So that one's pretty straightforward, but some other ones are a little tougher to wrap your head around, like surface area. But that was that. The other thing which we did not get into fully, and this will wrap this up, is looking at the energy involved. So you'll notice when you look at these charts, and you'll see this in chemistry again, you've got a lot of arrows. We didn't really take the time to understand what all these arrows are, but there is one arrow I want you to understand, and that's the activation energy. So we talked about needing a certain amount of energy to get over this hill. So if we look at energy, you'll always see some sort of hill you've got to get over. And that's what that activation energy is. So sometimes, depending on what the reaction is, the energy within the system or the energy within the room is actually at the top of the hill already. So you have sufficient energy to have those reactants collide and form products. But with a lot of reactions that we've done, and you'll see, we do not have enough energy. So we actually have to add energy to that system to actually get to the top of that hill, because once we get to the top of that hill, then the reaction can continue and we see something happen. So that's what I want you guys to understand, is activation energy. So that pretty much does it. Again, there's some things in Learning Target 6 that we did not get into, so I'm not going to hold you guys responsible for it. And with Learning Target 7, again, only that one thing. So don't worry about Le Chatelier's principle. Okay, hopefully these screencasts have helped. Hope you guys are enjoying your last couple weeks of school, and hopefully we'll see some of you guys around next year. All right.